Thank you. Yeah, I decided to change it because I was initially going to give an overview, but 20 minutes was too little to give an overview. So I decided to talk in more detail about one of my recent works. The topic is Augmenting Mobile 3G using Wi-Fi, and this is joint work with Aruna and Ratul Mahajan at Microsoft Research. So we've heard a lot of talk since morning about how demand for mobile access is growing. For example, Nokia, a mobile phone company, has predicted that mobile data growth is going to grow 10 times faster than fixed traffic over the next 5 years. And mobile web is seeing an explosive growth. For example, AdMob, a mobile ads firm, has grown over 3 times over the last year. And this is not surprising given the massive adoption of mobile broadband today. So we've seen a lot of numbers thrown around since morning. The number I have here is that there are more than 900 million mobile broadband subscriptions today, and this is projected to increase to 4 billion by 2030. So the problem, however, is that mobile demand is projected to far exceed capacity. And again, the main problem for this, and we've heard this multiple times since morning, is that spectrum is limited. The current spectrum is about 409 megahertz. The total unallocated spectrum available, and here I'm including white spaces and I'm being very liberal about including white spaces, is about 230 megahertz. And the projected demand by 2016 is 800 to 1000 megahertz. So the question is, where are we going to get all this extra spectrum? And in fact, we're seeing manifestations of these problems even today. There's been a lot of news articles about this, but iPhones are basically overloading the AT&T network, and users in big cities are facing big problems because of this. And mobile providers are very well aware of this problem, and they are looking for ways to conserve spectrum. So the question seems to be that reducing cellular spectrum usage is the key to meeting this mobile demand. So how can we reduce spectrum usage? There are multiple avenues you could follow. First one of them is behavioral. For example, AT&T wants to educate their customers about usage. By this, they mean that they're going to present their mobile usage on a customer's cell phone in maybe to shame the customer. I don't know what the deal is, but that is the idea. And then there's economic, and I'm sure most of you read this, that recently AT&T decided that it's no longer going to support its unlimited plan, and it's going to start charging users for how much data they send or receive. And then finally is technical, where you can design protocols that specifically reduce the spectrum usage. And arguably you need more than one of these together to reduce spectrum usage, but this talk is going to be about some of the technical challenges that in reducing spectrum usage. So specifically, the idea is to augment mobile 3G using Wi-Fi. So Wi-Fis are available around us. Most mobile devices come with both a Wi-Fi and a 3G interface. So the question is, can I somehow offload my data to Wi-Fi so that I reduce the total amount of data that's being sent on 3G? And in this work, we specifically look at the vehicular mobility space, which is a challenging end of the spectrum compared to a stationary environment. And it's challenging, but another reason we're looking at it is also because there's been an increasing demand for vehicular connectivity, both from commuters as well as because of these navigation-based applications. So the basic idea is as follows. You have a vehicle, it's connected to the internet through a cell tower. When the user comes within range of a Wi-Fi access point, you shift and start sending data on the Wi-Fi access point. But of course, the problem is that Wi-Fi access point has much smaller range compared to cellular, and so soon the user is going to be out of range of this access point when it shifts back to cellular until it meets another Wi-Fi access point. And the technical challenges that we want to solve here is not about how is it that you should be doing this offloading, but rather, does this even make sense? So how much data can you offload to Wi-Fi? How much Wi-Fi capacity does a vehicular user see in a day? And also, if they can do that, can you do this offloading without affecting application performance? So that is the basis of our work. So our main contributions is a measurement study, which is a joint study of 3G and Wi-Fi connectivity to see if Wi-Fi can usefully augment 3G. And we conducted this across 3 cities. And based on this measurement study, we designed a protocol called WIFLR. This is a system that offloads data to 3G with respect to application constraints. And we deployed this on a 20-weekler test bed and evaluated it. So in the next remaining of the talk, I'll actually describe your measurement study as well as the design and implementation of WIFLR, starting with the measurement setup. So we have a few WIFLR nodes, and we have a computer inside the node. And this has both a 3G and a Wi-Fi interface. And a software simultaneously sends data both on 3G and on Wi-Fi on a per second basis. And the idea is to measure availability and performance. And we conducted the study in Amherst with 20 buses in the DieselNet testbed, with a 150 square mile area is the area that the buses operate in. And in Seattle and San Francisco, we used one car and we did VAR driving to collect measurement data. And yes?
Quick question. Why do you only send data? Do you download data?
We download as well, in both directions, yes. Yeah, I should have said send and receive.
Speed on 3G is very limited.
Yes, that's true. And we collected more than 3,000 hours of data over 10 days. And the first measurement result I'm going to present is that of availability across the 3 cities. So here we define availability as the number of seconds when I could receive a packet or send in either direction over the total measurement time. And so we sent 10 packets per second for this experiment. So you see that if you look at the 3 cities, the average 3G availability was about 85%. So it's not really close to 100%, not even, it's not 95, it's 85. And if you look at the average Wi-Fi availability, it's about 11%. Yes?
So you are only looking at public or Wi-Fi hotspots?
Yes. I was just going to come to that. So these are only with open Wi-Fi access points. And also, open Wi-Fi access points does not require a sign-in. So automatically you can connect to an internet.
I'm just curious, why don't you do it in a campus environment where you have Wi-Fi available?
So Amherst is a campus environment.
But it's not available all the time?
Well, because we're looking at a larger area, basically, because we also have to go. Yeah, so I have results for what happens if you just do it at an urban center. But it's not there right now, but it's in the paper that I can point you to, yes. In Amherst, we do, yes. I can point you to the data. But not in Seattle or San Francisco, we don't. Access point availability is quite dense, yes. Absolutely, that's the hope, yes. Yes. So the thing is this, for availability experiment, we just look at whether I received one packet over this whole second. So it doesn't really matter whether it's slow or fast, because I'm pumping data and I just want to get one, and I say, okay, the 3G was available that second. That was the definition of availability. So we can talk later if you want. So this 11% is a number that's from open Wi-Fi access points. So I think that was pretty high, much more than we expected. Of course, it's much less than 3G, yes.
What was the speed of the vehicle during these measurements?
It varies, actually. We did do a correlation study with speed and availability. There wasn't that much correlation, but it really varies because whether you're in the city or in the highway and so on.
And when you say one packet received, do you count the packets exchanged as part of acquiring the network and acquiring a TCP/IP address? I mean, an IP address?
No, actually, this was UDP, but we do not. It's a good point. Actually, we do not consider association. So once associated, you receive one packet.
So these are true payload packets.
Yeah, exactly. Yes.
So how extensive were these drive tests, and sort of what is?
So
San Francisco is, I guess, a big.
So San Francisco and Seattle, I have to admit, was not extensive because it was our own VAR driving. So we had this in the cars, and wherever the car went, we did the measurement. But in Amherst, it was much more extensive because it was 20 buses that go around a 150 square mile area campus, and I can show you the area that the buses go and to get an idea.
The Wi-Fi actually, these are some private Wi-Fi access points actually that simply are not open, or these actually sound like campus or Wi-Fi access point. And
So
actually are deployed in some sort of a pattern.
good question. So in Amherst, in the downtown Amherst area, we do have our own mesh access points that you could connect to that are open. But that contributes to, so it's about a 2-mile area. And so it's much smaller compared to the entire area that we considered. And in Seattle and San Francisco, we actually don't know what these access points are, except that we know that we could connect to the internet through them.
Was this where Seattle runs an open wireless mesh network in downtown area? Seattle wireless, was that where it was? In which case then?
No, in Seattle it was more Redmond and Seattle together. So I actually don't know about Seattle that much because I did not do the war driving. So okay. So the point though here is that Wi-Fi availability is only 11% compared to 85% 3G availability. And then did performance measurements. So let me first present the loss rate measurements. So here the x-axis is the packet reception ratio, which means 0 means that no packet was received and 1 means all of the packets were received. And again, I've sent 10 packets per second. So you see that Wi-Fi loss rate is actually much higher than 3G loss rate. So 28% of the time, almost no packets were received on the Wi-Fi interface, while less than 8% of the time, no packet was received on 3G. And similarly, if you look at throughput, again, Wi-Fi throughput was lower, at least median throughput was lower. And by throughput here, we mean the total data received per second. And for this experiment, we actually blasted packets in the hope that we were exceeding capacity of the link, so that we can actually see how much total data was received. So here, the x-axis is the UDP throughput. So if you look at upstream, the median Wi-Fi throughput was about half of that of 3G. And this was true in the downstream direction as well. The median Wi-Fi throughput was half. But if you look at the last 20th percentile, Wi-Fi throughput was better than that of 3G, yes.
Have you correlated these results with the vehicular speed?
I think
for
we
buses, I would suggest that this reflects the situation for buses because at higher speeds, Wi-Fi really performs poorly. However, for pedestrian speeds, Wi-Fi will be in business.
I'm not so sure. So what we did do indoor experiments and saw that actually Wi-Fi throughput was much, much higher than 3G throughput. That I agree. But I suspect that this problem was not just because of mobility, but it's also because just of the outdoor environments and the fact that these Wi-Fi access points are inside. So I'm not so sure that speed is the only reason for this. Okay, so we also did a lot more measurement studies to look at the temporal, spatial distribution as well as correlation with speed and so on. But I'm not going to talk about those here. Just that the implications of our measurement study is that if you used a straightforward design of just used Wi-Fi whenever available, then you could only offload about 11% of the data because that was the availability. And you could hurt application performance because if you keep switching to Wi-Fi whenever available, both because of higher loss rates and lower throughput, this could be a problem. So to combat this, we designed WIFLR. And WIFLR uses two key ideas. First, because Wi-Fi is available, if you use Wi-Fi only when available, you cannot really offload that much data. We exploit application delay tolerance and wait to offload to Wi-Fi. So for example, some applications are naturally delay tolerant, email. Now if my email application can wait for 30 seconds, I would wait to see if I have a Wi-Fi offload opportunity in those 30 seconds. And I use a prediction-based offloading in that I would first predict whether Wi-Fi is going to be available in 30 seconds and only wait if it's going to be available. Otherwise, I immediately start sending data on 3G. So in other words, I only delay applications if I'm going to have 3G savings. And on the flip side, if I used Wi-Fi whenever it was available, it can affect performance of applications such as mainly delay and loss sensitive applications such as VoIP. So here we use fast switching to 3G when Wi-Fi performance becomes poor. And the main point here about fast switching is that it has to be done at a really small granularity of a few tenths of seconds if you want to support something like VoIP.
Just a quick question. I assume that on iPhone you cannot switch to Wi-Fi by yourself.
Yes, so I have to have, like, full disclosure, we do this for a vehicular setting where we have a computer and we do all of the implementation on a laptop rather than a mobile phone. So, yeah. So these are the two key ideas, the prediction-based offloading and fast switching. So let me go through each of these quickly. The way prediction-based offloading works is that if D is your delay tolerance threshold, so 30 seconds you can wait, for example, and S is the remaining data to be sent, then Whiffler would do this every second. It would see whether Wi-Fi is available. If it is available, it will send data on Wi-Fi. Otherwise, if W is less than S, where W is the predicted Wi-Fi capacity in the next D seconds, and S is the remaining data to be sent. If W is less than S, then you send data on 3G. Otherwise, you wait for Wi-Fi. And the way you predict Wi-Fi capacity in Whiffler is to use a simple history-based prediction to predict the number of access points you meet in the next D seconds based on the last n encounters. So we use 4 as a number. And this is based on our measurement where we found that future AP encounters really depends only on the recent past. And then once you know this, the Wi-Fi capacity is the expected number of APs you meet times the capacity per AP. And again, capacity per AP we calculate using a history-based method. And we found that this simple prediction actually yields pretty low prediction errors. And so the results are in the paper. And in fact, if you used a more sophisticated prediction using an AP location database and user mobility combined, you do better, but not that a whole lot better. So you can get most of the way there using a simple history-based prediction. Again, I'm not going to show you results for the sophisticated prediction, but it's there in the paper. So, okay, let's move on to fast switching. Remember here the idea was that you want to switch to Wi-Fi if 3G performance, switch to 3G if Wi-Fi performance becomes poor. So the algorithm is that if you do not have a Wi-Fi link layer acknowledgement within 50 milliseconds, I switch to 3G. And the motivation is that if I don't receive a link layer acknowledgement within 50 milliseconds, it probably means that the first packet was lost. And of course, Wi-Fi is going to retransmit the link layer, but it can take arbitrarily long, and that can affect performance of VoIP. So instead, you switch to 3G.
I think in the beginning you mentioned that you were running 802.11b, right?
That's right, yes.
So if you have any access points which run on 11G only mode, they will be kind of hidden from you.
That's true. That's true.
So if you would allow B/G, you might actually increase the fraction of Wi-Fi nodes which are available.
That's true. I have to actually get back to you on that. I think that is true, but I'll get back to you on that.
Well, it sounds like I run G only.
Yeah, I have a feeling that maybe, yeah, I don't know. And so that is the basic idea. We implemented this in our test bed. So like I mentioned, each vehicle has two interfaces, a Wi-Fi and a 3G interface. And so the Whiffler software running on the vehicle would decide whether it wants to send the data on Wi-Fi or on 3G. And we also have a Whiffler proxy to sort of manage IP addresses, data coming from different IP addresses. And we actually do the offloading both in the upstream and the downstream direction. But for downstream, what we do is that the Whiffler software in the vehicle again decides whether it wants to receive data on the Wi-Fi or the 3G interface, and then it lets the proxy know, and then the proxy sends accordingly.
Just a quick comment. The video consumption is the biggest thing, and then that thing you cannot wait. You don't want to watch a video, you want to watch a film.
True, which is why we have the fast switching. The fast switching was precisely for applications like video or VoIP. We did not do our experiments with video. One of the reasons was we chickened out because with VoIP we had this MOS, a mean opinion score, which we could figure out what the quality was. With video we didn't have something handy like that, which is the reason why we didn't do video experiments. But yes, that's why we have the other part. There are only certain applications that are delay tolerant. For the rest, you can't really use that.
What is the median average connection for each access point?
In Wi-Fi, it's about 20 seconds. And so for fast switching, we implemented this using a low-level signaling mechanism where the driver will let us know whenever it receives a link layer ACK. So, and we've evaluated this on our test bed by deployment, and we also ran trace-driven simulations to do a more broader study. So let me first present some deployment results. For some reason this is crooked, but so our with the prediction-based offloading, we used the application we used was file transfer, the 60-second delay tolerance, and 30% of the data was offloaded, compared to 10% if you only used Wi-Fi when available. And fast switching we did with VoIP. So here there were 20 byte packets every 20 milliseconds. If you look at the percentage of time that the VoIP quality was good, it was 68% when we used Whiffler, compared to 42% if you used Wi-Fi when available without caring about performance. And in our trace-driven evaluation, we first validated our trace-driven evaluation to make sure that the results we get are similar to what we got in our deployment. And then we also vary different things, the workload, the AP density, and so on, and look at several alternate strategies. Here I'm only presenting two. One is using Wi-Fi when available. The other is an oracle scheme that does a perfect prediction of how many access points you meet by looking in the future. So the idea is to basically get an upper bound of how well you can do. And so this experiment was for varying delay tolerance threshold. And the y-axis is the fraction of data on Wi-Fi. So the more the fraction of data on Wi-Fi, the better it is because you're reducing 3G load. So if you used Wi-Fi only when available, you would only get 14% of data is offloaded to Wi-Fi, compared to 42% if you used Whiffler. And if you use the oracle scheme, you'd actually do better than Whiffler, but not a whole lot more. So it comes pretty close. And of course, one of the things about Whiffler is it adds application delay. Oh, I forgot to mention that these are for web traces that we obtain from commuters, like people in the vehicles who connect to the internet. This was from Microsoft. And we found, yes.
So this is a result of the trace-driven simulation.
That's right, yeah.
You cannot include the fast switching.
This is separate, yeah. We do two separate experiments. One is for delay-tolerant applications. The other is VoIP-like applications. VoIP-like applications where you use, I'll present the results for that too. And so we found that Whiffler actually increased the application delay only about 10 seconds over optimal because we do this whole prediction. And the next is for fast switching. So here this is for delay loss sensitive applications. So we look at VoIP. The y-axis is the percentage of time that the VoIP quality is good. And the x-axis is the switching delay. So how long do I wait until my Wi-Fi performance becomes poor before switching to 3G? So first notice that if I only use 3G, I don't use Wi-Fi at all, my VoIP quality is good only about 58% of the time. If I combine Wi-Fi and 3G, but I don't care about, I always use Wi-Fi when it is available, this becomes lower in that only 40% of the time is the VoIP quality good. But if I used Whiffler and I used a switching delay of less than 40 milliseconds, the VoIP quality is good about 73% of the time. So the reason for this is that Wi-Fi has a lower round-trip delay. So if you use Wi-Fi when it has a good quality, VoIP performance actually gets good. But if you persist with using Wi-Fi even when the performance is poor, then you lose the quality. This is again simulations.
How are you actually implementing the fast switching?
Using a mad Wi-Fi driver, it lets us know. We have a signaling mechanism. It lets us know whenever it receives a link layer ACK.
Excuse me, I have some difficulties understanding 58 versus 73. So you're saying only 11% of the time you have Wi-Fi available at all.
Oh.
So how could it drive the gain by like 20%,
Oh,
which is on a relative scale is like 50%?
Sorry, I should have mentioned. This was done in the urban center. All the VoIP experiments are done in the urban center.
So it means the fraction of Wi-Fi
Is much
substantially
higher.
higher than 11%.
Yes.
Okay.
Yes, sorry. I should have mentioned that, yes. And not only does Whiffler improve VoIP performance, but also 30% of the data was offloaded to Wi-Fi in
So
this
if,
experiment.
for example, one would use 11% as the kind of a baseline, would you still see 73%?
No. No, we will not.
So you're saying the optimal is only 73%?
Yes.
I don't know of any cellular network that has such poor voice quality. I mean, they are engineered to be pretty good.
No, right. This is for VoIP though, right? It's not.
VoIP over 3G.
Yeah. This was actually the results we.
Acceptable results for any operator sees this will immediately innate.
This is the result I'm getting. I mean, it depends on what you define VoIP quality as too, right? Like we defined a particular MOS score, and the way we are doing it is that if for a 3-second interval is the MOS score greater than 3.5. That's the way we define VoIP quality. But that sounds like.
I think the issue is that these are networks are designed for data, not for voice. This is not cellular network that actually make you.
This is 3G data. They're talking about 3G.
No, but this is for VoIP.
This is VoIP.
You do voice over voice, over circuit. You don't do voice over voice.
Okay, all right.
We also do other. Yeah. Yes.
So I was going to ask, like you could, there's protocols out there that today will do a mobility between Wi-Fi and 3G, granted not anything nearly as fast. Have you compared with those protocols?
You mean protocols that do offloading between or handoff between Wi-Fi and 3G?
Well, you could think of handover from
Yeah.
Wi-Fi to 3G and back as a form of offloading. It's much slower than this, but
Yeah.
it would be interesting, I don't know if you've done it, to see what the benefit of this kind of a fast offloading is compared to.
We don't do that. We do not do that for the offloading the previous case because that was orthogonal. But I agree. In this case, maybe it does make sense to do that just to see how fast it is. But we did not do that.
So I hate to do this, but
Yes, sorry.
lots of questions. So
Yeah, just 2 more slides. So some of the things that we want to do in the future is to look at energy issues because right now we don't because this is not, we're looking at laptops and not mobile phones. And the other is also like using some sort of prediction and accessing data over Wi-Fi so that you can actually reduce 3G load further. And in conclusion, augmenting 3G to Wi-Fi can reduce pressure on cellular spectrum. And however, our measurement study shows that low availability and poor performance of Wi-Fi. So to combat this, we designed WIFLR that uses prediction-based offloading and fast switching. This work will be presented at Mobisys this year in a couple of weeks. Thank you.
I'm canceling all questions and move on. We asked a lot of questions.